Hi students, it's Miss Vernon, and today I'm here to talk on lesson 2.3, day 2. We're going to take a look at modeling higher degree polynomials, specifically when they're in factored form. So yesterday you learned about how many extrema and how many zeros there might be, as well as the y-intercepts. Today we're going to take a look at that same information, but we're going to combine it with a couple more layers. Let's get started. So, as you recall from yesterday, we learned about working with polynomials that were in this form. So you can see that there is a polynomial here written. It is in standard form. Recall that standard form is when the highest exponent is listed first and everything else is in descending order. So we would call this the leading term. And from the leading term, we can determine that the degree of this polynomial is 6. So I write that as a degree 6 or D6, just for my own knowledge. Next, we can identify the y-intercept very quickly when it's written in standard form, as the y-intercept means plug 0 in for all the x's, and what do you get out? So if I plug in 0 for all the x's, I would get 0 to the 6th, which is 0, 0 to the 4th, which is 0, 2 times 0, which is 0, plus 9, which basically tells me my y-intercept is 9. Next, we want to determine the end behavior. Again, the end behavior is connected to this term that I have in the box. And because the leading coefficient is positive, so I'm going to say a positive LC or leading coefficient, and that the degree is even, I can know that our end behavior is going to be the same or going the same direction. And because it is positive, I know that my end behavior is positive infinity and positive infinity. Now, in formal notation, I would say the limit as x gets really small is going to go to positive infinity. So that's in limit notation. And then I can do the same thing. The limit as x gets very large is also going to go to positive infinity. Okay, sometimes when I'm doing my shorthand, I'll use the arrows to denote the end behavior, but in formal writing, I would use my limit notation. Right? I know that because it's a degree 6, that I can know that there should be at most, so again, at most 5 max or mins, and I will have at most 6 zeros. What this means is that I don't have to have that many because some of them could be imaginary or complex. Therefore, I won't see them all. I went ahead and graphed this function, and this is the x-axis. As you can see, the graph never crosses it. Therefore, none of my zeros are going to show up when I solve because they're all going to be imaginary or complex. I can't see them on the graph. So step 5, identify my zeros or x-intercepts. I can't do that in this case. Let's take a look at different ways to work with these functions when this happens. So in our first example, we are given this polynomial, and I'm asking you to basically analyze it and sketch it. So starting off, I always like to check, is my polynomial in standard form? And it is, so I'm going to put a box around my first term. From my first term, I know that this is a degree 6. Oh, sorry, a degree 3. I apologize for that. And I also know that the leading coefficient is positive. It's actually an invisible 1 sitting in front of that. Because it's a degree 3, I know I could have at most 3 zeros. That means I don't have to have 3 zeros, but I could have up to 3. Now, because it is a degree 3, my end behavior is opposite. Odd functions have opposite end behavior. That means that normally it would be a negative positive. What this means is the limit as x gets very small of our function, our graph is going to approach negative infinity. And what this arrow means is the limit, or as x gets very large, our y values are going to approach positive infinity. Okay, so that's what the arrows mean. That's kind of what are the tails of the graph going to do. Next, I'm going to find my y-intercept. Again, I usually start with these things because they're pretty quick to identify. And so I'm going to go ahead and plug in my 0, and I got 0 to the third plus 2 times 0 squared minus 11 times 0 minus 12. So 0, 0, 0. That means I got negative 12 out. My y-intercept is happening at 0, negative 12. So really, I don't have a ton of information that I can graph. I don't know how to factor this yet, but it's coming, don't worry. Not today, but very soon. And so from what I do know, I can graph the following things. I can graph my y-intercept. Let's go count by 2s. So 2, 4, 6, 8, 10, 12. So I have my y-intercept here. And I know my end behavior. So I can have it cross the x-axis. 1, 2, 3. I don't want it to cross more than 3 times because I know that there's at most 3 zeros. So I'm going to go ahead and say, this is what my sketch is going to be. Is it accurate? Probably not perfectly. But as we move forward, we're going to learn more skills to create a more accurate graph. Let's take a look at the next example. On the next example, it says find the zeros by factoring and then using the zero product property. After you've factored, analyze the polynomial and graph it. All right, well, let's take a look. We are not used to working with degree 3, but it says we can factor it. So let's give it a try. As I look at this polynomial, the first thing I notice is that all 3 terms have a common factor, and that common factor is x. So I'm going to pull out an x, which leaves me with x squared minus x minus 6. Next, I want to say, can I factor this quadratic further? And as I look at it, I recognize that I can indeed factor this more. Now, for those of you who are still using the magic questions, go ahead on the side and create your sneaky square to do your factoring. I know that the top box is x squared and the bottom is negative 6. I'm looking for terms that add to negative 1 and multiply to negative 6. Pretty quickly, I see that negative 3 and positive 2x are going to add to negative 1 and multiply to negative 6. I can finish the factoring and I get my remaining 2 terms. So x minus 3 and x plus 2. Now, I like to use a combination of these 2 forms of my polynomial to analyze my function. So first thing I notice is that it was a degree 3, and after factoring, I could identify that I have 3 zeros. My 3 zeros are going to be happening at x equals 0, x equals 3, and x equals negative 2. So I want to make sure I plot those points. Remember, these are the places where my graph is going to cross the x-axis. So I'll go ahead and put those in right away so we don't forget. Next, I like to find my y-intercept because that also adds more accuracy to my graph. In this case, I'm going to plug in my 0 to the first function. And when I do that, I get 0 to the third minus 0 squared minus 6 times 0. In this case, I get 0 out. That means my function will cross at the point 0, 0. It happens to also be the x-intercept. Next, I want to figure out my end behavior. I sometimes use the shorthand EB for end behavior. So because it's an odd function or an odd degree, I know the end behavior is opposite of each other. That means normally it's negative infinity and ends at positive infinity. I always want to double check that that leading coefficient is positive. If it's positive, this is true. If that leading coefficient were negative, I would have to switch my end behavior. But we're good to go. So we have our degree, we have our zeros, our y-intercept, and our end behavior. We're now ready to sketch what this graph looks like. I know it needs to end down here. Oops, let me go ahead and try that one more time. So it's going to go this direction. I know that over here, it's going to end up going positive, and the stuff in the middle, I got to kind of put the puzzle together. So it's going to have to go below and then above the x-axis. There you have it. We've sketched our graph. I have 2 more examples for us. Well, 2 more points of conversation to have with you. And the next one is on multiplicity. So far, we've seen linear factors. A linear factor means that the factor is a linear factor and its exponent is no greater than 1. In this particular case, we have factors that have exponents that have different amounts. These different exponents are going to have our x-intercept behave differently. So let's go ahead and take a look. So when we have a factor that has an exponent, we say that that exponent or that 0 has a multiplicity. So in this case, I would say that at x minus 2, when I set that equal to 0, at x equals 2, that factor has a multiplicity of 3. The reason that has a multiplicity of 3 is because the exponent on that factor was 3. Now on our graph, this is showing up right here. It's crossing at the value of x equals 2. And notice it's not just going straight through like we saw in the previous problem. It's kind of pausing there. Okay. When this pauses like that, we say that it is hugging the graph. Think of like, come in for a quick hug, you pause, and then you move on. You're headed out the door, you give your mom a quick hug, and then you move on, right? So that's a multiplicity of 3. We paused, we hugged, we moved on, right? Now, we also have a multiplicity on this next factor. So the next factor is x plus 1. If I set that equal to 0 and do our solving, I would say that I have 0 at x equals negative 1, and that this has a multiplicity of 2. The reason I say that this has a multiplicity of 2 is because the exponent on that factor was 2. Notice that this shows up on the graph like this, right? Now, this is what we call a kiss. I like to give the analogy of like elementary school. Someone dares you to kiss somebody on the cheek at the playground, so you run up to them, you kiss them on the cheek, and you run back away. The graph will approach the x-axis, it will touch it or kiss it, and then it runs back away. We never cross the x-axis with an even multiplicity, but we will cross the x-axis with an odd multiplicity. Okay, so let's go ahead and take a look at some other facts that I have. So if the multiplicity is greater than or equal to 2, then it is said to be a repeated 0. That means that 0 is showing up more than once. If the multiplicity is even, so even multiplicity is what I showed you second, this is the kissing of the x-axis. Note it will not cross the x-axis, it just touches it and then runs back away. If the multiplicity is odd, other than 1, remember 1 will go straight through, but if it's odd, we say that it's going to hug the x-axis. So it goes in, it pauses, and then it moves on. If you add up the multiplicities, you will get the degree of the polynomial function, and the degree will help you determine the end behavior. So in this case, I have a multiplicity of 2, and I have a multiplicity of 3. If I add up those multiplicities, I would say that my degree is 5. That means my end behavior is opposite. So negative infinity here and positive infinity here. So again, remember, I use those arrows as shorthand for end behavior, but it really is just referring to as x gets very small, I list first, and as x goes to positive infinity, I list that second. All right, I have 2 more examples for us. I know, hold on, this is a little longer of a lesson. So in the next problem, we are basically going to analyze a function that has some repeated multiplicities, or some multiplicities in general. So I'm going to go ahead and begin. It says state the degree and determine the end behavior. We need to identify the x-intercept, sketch the graph, and create a more accurate graph by finding the y-intercept. So just kind of listing out everything we'd want to do. I like to find the x-intercepts first because I find that to be a good launching point. So I'm going to go ahead and set each one equal to 0. So x equals -2, and I'm going to go ahead and put an M3 next to it, indicating that this is a 0 or an x-intercept, and it has a multiplicity of 3. Therefore, it is a hug of the graph. Then I have x minus 1 equals 0, so x equals 1. This is a multiplicity of 2, and a multiplicity of 2 means we're going to kiss the graph. Last, we have x minus 4 equals 0, so x equals 4. And this has a multiplicity of 1. Now, why do I write an M1 after it? Because it helps me not to forget it when I go and add them up. So this is going to go straight through the x-axis. It's not going to hug, it's not going to kiss, it's just going to pass straight through. So next up, I'm going to state the degree. Now, I know I'm kind of doing this in a slightly different order, but the degree of this polynomial is going to be 3, 4, 5, and 6. This is a degree 6 polynomial. Now, it's a degree 6, and the leading coefficient is going to be positive. I know this because there's no way for x to the 6th to become negative, as there's no constant being multiplied through that is negative. So therefore, it's impossible for it to become negative. Because it's an even degree and the leading coefficient is positive, I know my end behavior is going to end up positive, positive. The last thing I do always want to find before jumping over to the graph is my y-intercept. And to get that, I'm going to plug in 0 for all my x's. So I'd have 0 plus 2 to the 3rd power. I'd have 0 minus 1 squared, and I'd have 0 minus 4. So I have 2 to the 3rd power, which is 8. And I have negative 1 squared, which is 1. And I have negative 4, which is negative 4. And 8 times 1 is 8, and 8 times negative 4 is negative 32. So I also know that I have a y-intercept at 0, negative 32. Now, are all these notes going to be helpful as I start to graph this? Absolutely. I can't stress the importance of pumping the brakes, hitting pause, and taking your time to graph what you're seeing. So at -2, I know that this is going to be a hug. You might want to write an H near it just so that you can get an idea of what is going on there. At 1, it's a kiss. And at 4, it's going to pass straight through. So I know it needs to cross through the purple and blue dots. I also know that I need to end up here, and I need to end up here because my end behavior was positive, positive. So as I start to connect the dots and I'm approaching the first one, I do want to make sure that I see you pause. So notice I'm pausing, and then I have to go through this dot next. Otherwise, I'm not going to be able to connect to it. Kissing the graph means peck and run back away. And then I got to pass straight through 4 because it was just a multiplicity of 1. Now, students always ask me, Ms. Vernon, what about this? Does it matter where we end? It really doesn't. For what we're doing, we're looking big picture. Do we have a general idea of what this graph is going to look like? Absolutely. If you want to pause, go ahead and pause and take a look at it on the calculator. You're going to see you get the same function. So as we move forward, you're going to say, well, okay, I got to learn how to do this. I need to learn how to write it in factored form. You absolutely do, and we will in future lessons. The fourth and final concept I have for you today is, can you reverse it? If I tell you your zeros, can you write me a function? Okay, so in this case, I am giving you the fact that these are our zeros. Now, sometimes students get confused about how to work it backwards, but I encourage you, don't overthink it. Basically, what you're doing is you're moving the number to the other side. So x minus 2 becomes a factor. I subtracted 2 and got it reset equal to 0. X equals -5, I'm going to add the 5 over. So my factor is x plus 5. And x equals 9, I'm going to subtract the 9, so I got x minus 9. This would be my polynomial in factored form. Now, I do always encourage you, remember, don't forget to, if it says to write it in standard form, you're going to have to FOIL this out. What that looks like is you are going to have to multiply out the first 2 terms. So in this case, x times x is x squared. Outside is positive 5x. Inside is negative 2x. And last is negative 10. Combining my like terms, I would get x squared plus 3x minus 10. I'm going to take that and I'm going to multiply it by this x minus 9. So yep, you're going to have to do a couple steps of simplifying. Some of you for this one might benefit from multiplying it out in a box or a rectangle. In this case, I would use a 2 by 3. So we'd have x minus 9 and x squared plus 3x minus 10, filling it in and finishing the problem. See if I can do this quickly without making a mistake. The nice thing about this is it quickly allows us to organize our work and gets us to the point where we can write our final answer. Combining our like terms, which will be on the diagonals, we get x to the third minus 6x squared minus 37x. There we go, 37x plus 90. All right, there you have it. That is your lesson. I know it's been long, but hopefully you are tracking with how to work with polynomials when you have multiplicities. We'll see you soon. Bye.